So good afternoon. Are you able to hear my voice? My slides are visible, right? So good afternoon, everyone. So today we are in the seventh week of online problem solving session. So first will I introduce myself, Probir Maiti. So I am taking the course name is Introduction to Polymer Science and course instructors Professor Divakar Dhara. So earlier classes we have talking about the polymer, how we can synthesize the polymer. Then that then we differentiate the different type of polymers like that. Now today's classes we are mainly solving that after synthesis of polymer, how we can make that final product from the polymer. So there will be like various process to making the final product of the polymer, where which going to use in that last we used in that day-to-day life. So like how the polymer is starting. So first you have choosing some raw material. So maybe the raw material coming from nature, or maybe raw material coming from some mm, unit where like that petrochemical units. So where we are getting the polyethylene, ethylene, propylene like that. So from that petrochemical unit, so we are going to making that monomer unit. We are getting the polymer. So after polymer, so there will be various process to synthesize of polymer like addition polymerization, condensation polymerization like that. So after synthesis of polymers, now you are going to use this polymer you in your purpose. So to making the polymers useful, to making the polymer sheet or polymers material, so we have to process this polymer. So how we can process? So like polymers, with there will be two type of polymer, like we are called it thermoplastic polymer or thermoset polymers. Thermoplastic means that we can easily heat the polymers and they can melt. So maximum thermoplastic polymers. So we heating the polymer, it melt it, then we give the particular shape of this polymer. So like we want to use, like you want to make bucket, so you have to that use your polymer melt solution into the bucket, and it will be like making a bucket. Then after if you cool it, so it will become bucket. So maximum thermoplastic polymers, so you can reprocess it like that. If you're making bucket, then from that you can also you melt it this bucket, and you can give this in the another shape, like you want to make some hose or some pipe, so you can make it like that. So thermoplastic polymers means that can reprocessable, but after making final product you can process the polymers again. But when you're talking about the thermosetting polymers, so thermosetting polymers are not reprocessable, because in thermosetting polymers, so they are cross-linked to each other. Cross links means that polymer chain are are not easily is for when we are heating it, so polymer chain are not passing each other. So like they are behave like a solid material, because in thermosetting polymers the due to the cross linking, so it will be the chains are bind to each other like this. So this is your cross linking point. So when there will be cross linking, so it will be not, this chain are not movable to each other, so you cannot make this polymers further processable. So after making your product, so it will be final product, so you cannot reprocess it. So there will be various technique where we can use this polymer to make the final product, like such example like compression molding. So compression molding, like it's looking like this instrument. So here we give that our polymer sample here. So then there will be some upper mold and the lower mold, then we press it. So after pressing it, so press and heating, so it will be become the melt, and the press size will be detect that final shape of the polymer. So then you get that final product. So this and like this an example of the compression molding machine. So there will be upper mold, there lower mold. So you place your polymer sample here, then you press it, like upper mold is coming down. So from this here, so you can press some pressure and you apply some temperature to mm, become its melt the polymer, then it will be get the final shape of this material. So like you can make that like tire which are generally made by this compression molding machine. So where that different shape of tires are giving here, and finally it will be cross linked there and it will get that thermoset polymers. There will be another technique we can reprocess the polymer, like calendaring. So in calendaring mainly there will be various role is present. So in this various role we can pass that mainly that fibers, and sometimes we add some rubbers also into there. So after that it will be become that a calendaring, so that your material becomes smooth after various type of roll when passing through this material. So then another technique like that extrusion molding. So in extrusion molding what will done, there will be some feed hoppers. So it will be coming here, and due to there some mold is there, so it will be when that material is goes here. So due to this is rotating. So after this when it will be rotate, so polymers become melt and then rotating, and at this temperature. So what I am talking about, like extrusion molding. So extrusion molding, that your polymers you add here, and there will be some rolling is there. So when the polymer is going from here to here, so that the sizes between this the two piston are lower. So then the polymer when going to passing through here, so they face some friction between this wall and this that roller. So when they are facing friction, so due to this friction, so they become viscous solution. So after that at that heating condition and rolling, so that viscous material passing here, so they become that liquid polymer solution, like polymer melt solution. So then you give this into the particular shape, like you can give that if there will be some. So you give as choosing your particular shape, so you can get your final product. So for that polymer that when you're talking about that shear rate, like here that we are applying the shear rate into the polymers and it become a viscous melt solution. So depending upon the shear rate, that instrument have the different shear rate in different instrument. Like in the compression molding, the shear rate is around 1 to 10 second inverse. The calendaring is 10 to 10 to the 2 second inverse. So different shear rate are facing in different instrument. So when we are more complicated instrument like extrusion, injection molding, so they are facing more shear rate. And when we are talking about compression molding, so when there will be only that that upper piston coming and it will be getting pressurized, so that will be lower shear rate are facing. The calendering is shear rate is high, as there will be many a roll are present, so shear rate becomes high. But when it will be coming the extrusion injection molding, the shear rate is more high there, and they become the polymer melt solution. So between that difference between the extrusion and injection molding, so generally the extrusion molding is generally used for that large type of product like tubing, or you can make that extrusion mold blow molding, you can make the product like bottle like that. But when you come to injection molding, so you have that more integral particle design, like you need a small product with some various design, so you can make by this injection molding, so it will be more complicated instrument as compared to the extrusion blow molding. So when you that polymer is melt, so there will be they have different viscosity uh, during the different shear stress or shear rate. So the viscosity, if the shear stress and viscosity plot is like a straight line, so it will be follow the Newtonian behavior. So the shear stress and shear viscosity, with increasing the shear stress, the shear viscosity is increases. But there will be some non-Newtonian fluid like that, so it will be like dilatant or pseudoplastic fluid. So where that with increasing for the pseudoplastic, so with increasing the shear stress or shear viscosity is down, uh, and for that shear dilatants, for dilatant non-Newtonian fluid, so with increasing shear stress, shear viscosity is increases. But for the non-Newtonian, so it will be behave like a straight line. So any plastic, when you are melting that plastic, so it will be maximum behave like a non-Newtonian fluids, not like a Newtonian one. So that first question is that consider the following polymer processing process. Identify the process that is associated with the lower shear rate. So who is going to the lower shear rate? So that calendering, so it will be that shear rate high. Injection molding also the higher shear rate. Extrusion also higher shear rate. And compression molding which have the lowest shear rate. So if you go into that shear rate, the compression molding, the shear rate is around 1 to 10 second inverse, where the calendar extrusion are more higher shear rate. Then after, if you make that your polymers material, then you do you want to check that polymer material how it will be look like when you apply in this polymer material applied the load. So how this load bearing capacity of this polymer, how it will be look like. So for this reason we have done some experiment, like we called a tensile testing. So from the testing we can get an idea about that polymers, so how the polymers will be look like. So up to like when there will be polymers, so when if we applied stress, it will be coming back its original position. So then it will be some elastic behavior. So when you increase the load, so like that there will be two piston, like about pistons, and that lower pistons which is connecting your polymer sample, and from the upper pistons, so it will be applied load and it will be goes up. So when it goes up, so like up to some points, like if you release the load, so it will be come back. So like these shapes are remain same, it will be come back its original position. So up to that part it is called that elastic modulus. So after elastic modulus, so if you more applied that stress or applied load into this, so the polymers become more and more deformed. So when that they are more and more become deformed, so there will be some non-elastic modulus, like the polymers become break, or the polymer become straightened. So they are the non-elastic material, so it will be never come back its original positions. So if you applied the load, and after load is load is released, so it will be not never coming its original position. So then it's called that non-elastic mode. So then then the certain point is coming, that yielding point. So yielding point at yielding stress, like this point is called the yielding. So up to this temperature the polymers comes into this position, but it takes some time. But after that there will be some plastic deformation. So in that plastic deformation, so it when the polymers become deformed, so it's never come back to original position. And for some polymers it will happen that some strain hardening, like when you apply stress in the polymer sample, like a polymer plastic like sample. So like when you applied the stress, sometimes it will happen that your polymer chains become more and more oriented when you applied stress. So when they are become more and more oriented, so then that will be happening, that's strain hardening. So you need more stress to break it. So and after that some points is coming. So when that polymers become ultimately break, like that the two the between the two piston, the polymers that from the middle or some that points, it will be break from one to one. So it will finally break that breaking point or ultimate stress strain you can get. So by this plot, stress strain plot, we can get an idea about that how the polymer will be look like. Does it behave like a elastic materials, or does it behave like a plastic materials, and how much load it can be sustained up to the up to that breaking is happened. So from this idea we can get an idea about that polymer sample and polymer's properties. So so the next question is like that. So you have to find out that uh, which the points is corresponding to what. So you clearly shown this, the first point is related to that yield point, and the second is the break point. So that your right answer should be this one. The first is the yield point and second is your break point. And this the strain hardening, so it will not mentioned here. Then the next question is the time dependence elongation are measured by which experiment. So here that first I will discuss about that how the experiments is look like. So stress relaxation means that you applied some constant strain, like constant strain into your material. So how this material release its stress, so that will be measured by this stress relaxation experiment. So creep test is like that, you have the materials and you applied some load each here, so some applied load each here. So creep test is suggest that how that elongation happened if you applied some constant load into this material. So how this material will be behave, like that how the elongation will be behave. Then the fatigue test is coming. So fatigue test is that if in your material, if you applied some cyclic stress, like you applied some stress, then you release it, then you applied some stress, then you release it, then after that what will be happening to this material, how this the material becomes, how much strain, that difference between this original material and that after cyclic test cyclic stress is applied into this material. And there will be another measurement like the hardness measurements. So hardness means that how your material would be hard, like, so it means that the resistance to indentation, like when your needle is coming into this material, so how this your material become hard, that can resist this indentation or some breaking of this material. So here that your uh, talk like that time dependence elongations. So time dependent elongation, so it's that test is like that creep test, so where we can apply some constant load, and during this constant load how is your material behave like. So this test is given by the creep measurement. Now the next question is that selected energy changes associate with that following process like elastic deformation and inelastic deformation. So when we are talking about the elastic deformations, that means when we applied load into this material, so material become, so like earlier material will be like this, so after applying load, now the material will be elongate. But when you release the load, if the material is come its original position like here, so it will be become that elastic deformation, so there will be nothing deformation will happen which is permanent. But when the inelastic deformations comes, so if you applied the load into this material, so material become deformed. But when you release the load, so some deformation is still into this material, so it will be not come back to its original position. So that is that inelastic one. So when you're talking about the elastic deformation, so what energy? So you are not losing anything. So you are that original position it's come back. So there will be no loss of energy during this elongation or during this deformation. But when there will be inelastic deformations, so inelastic deformation means so where you are losing some material properties, so you are losing some energy of this material. So that is called non-elastic deformation. So in elastic deformation, you are no loss in energy, but in elastic deformation, you lose partial energy. So that this will be the right. So the D, there will be no loss of energy in elastic deformations and partial loss of energy in elastic deformation. So like the elastic deformation is said to have that happened, the material returns to its original one. So the releasing the stress, the following same strain curve that will be during the deformation, so no loss of energy. But in elastic deformation, so it will be not coming its original state, so you are losing some partial energy here. Then for the semi-crystalline polymers, so we are getting some Tg and Tm of this material. So how the Tg and Tm of this material, like if the polymers material, so you have the polymer sample, and in that polymer sample, like if you're talking about the polyethylene, so polyethylene, so there will be various type of polyethylene like linear low density polyethylene, HDP polyethylene, like that. So that in that polymer, so there are some chain which is the bigger chain and some chain which is that present in the side chain, like that. So there will be some energy like there we, when we heat this material, your polymer sample, so what will happen? So first, if you heat this material, so first the vibration will be happened, like your vibration will be happened in between this, if a polymer making the CH bond or something, so vibration between that bonding. So if you first heat it, so the vibration between that carbon and hydrogen, so it will be start vibrating. So after that, if you are heating this polymer sample more and more, then your small side chain start to vibrating or start to moving to each other. So after that, if you are applied more heat into that polymer sample, so then a temperature is coming, so where your polymers become glassy to rubbery. That means that polymers now, the polymer chain start to move to each other. Like if you applied this temperature and if you applied some stress here, you can that polymers become trying to move, so you can elongate that polymer. But before that temperature, so like that glassy, so you applied load, the polymers become brittle, so it will be not the polymer chain not at all moving. So if you applied load, so it will be break. But after Tg, so it will be become rubbery, so the polymers start moving to each other. So that Tg temperature of the polymers is very much important, like where you can use this material. Like if your polymer sample which have the temperature the Tg is around 10 degrees centigrade. So if you applied this material in our country, like where the temperature is like generally above 20 or 25 degrees centigrade, so your material is like a rubbery material. So like like you can apply this material here. But if same polymer, if you used in that some country like Siberia or somewhere where the temperature is very low, like minus 10 degrees centigrade, so then that your polymers become rubber, that glassy there, so you cannot use your polymers there. So your polymers need to be flexible. Like if you want to some plastic material, so you know, and you want to make that some carrying load into this polymer, so if you take this polymer into this Siberian region or some where that that Tg, when it's the temperature is very low, that it will be lower than its Tg temperature. So now the polymer become brittle. So if you take it and you push some load there, so it will become break and it will be brittle, so you cannot use it. So for polymer solution, the glass transition temperature is very much important for your application wise. Then after that, if you heat that polymers into that, so then the polymers become melts like that. The polymers become now change its states from that solid to liquid. So melting means you changes its states from that some states solid to liquid or liquid to gases. So here that melting temperature means, so it will become that your rubbery to a viscous solution or yes uh, liquid solution. So for that polymers, these two temperatures very much important, the Tg and Tm. So Tm it tells that how much thermal stability it can withstand into the polymers. Tg will tells that how the polymers behave, like it will be behave like a rubbery or glassy. So this Tg, which is that Tm, which is that the first order change of Gibbs free energy, but when we're talking about the Tg is that second order Gibbs free energy, that when you see the equation of the Tg there. So there will be some instrument like DSC, that dynamic sorry DSC instrument, so where you can measure that your Tg and Tm of that polymer solution. So in DSC experiment what we are doing, so in this experiment, so there will be some pan. So in this pan we put some polymer sample into this pan, and another sample where we are not putting our polymer solution, so there will be some air. So when we are heating this polymer, so after heating it the polymer changes its states, so that will be needed some energy. So you can measure this del H, that enthalpy, how much enthalpy is needed for this polymer. So between these enthalpies we are getting like a plot, or if you, so there will be some plot like del H versus your temperature. So at what temperatures your polymers, like there will be some straight line shift, so that temperature we called it that Tg temperature. And and where there will be permanent shift is there, so that temperature we are called that Tm temperature, that melting temperature. So permanently we are getting some curve there. So we are called this melting temperature. So from this DSC experiment we can measure the Tg and Tm temperature of your polymer sample. So like and for this when you're talking about that crystalline material like small molecules, so for crystalline, perfectly crystalline materials we are getting only the Tm temperature, but when you're talking about semi-crystalline polymers or semi-crystalline materials like your polymers, so they have that both this temperature Tg and Tm, and these two temperatures are more needed to for that getting the polymers property, when we can get an idea about the polymer property. So like this, the Tg, which is the second order derivative and of the Gibbs free energy, and the Tm is the first order derivative of the Gibbs free energy. So the right answer will be Tg is second order and your Tm is the first order. Now we have, if you the next question is that you have to the value of glass transition temperature you want to predict. So there will be given the polyethyl methacrylate, poly-N propyl methacrylate, polybutyl methacrylate. So with increasing that ethyl to propyl to butyl, like with we are increasing the CH2 unit into that polymer. So like butyl there will be 4 CH2, propyl 3 CH2, ethyl will be there will be 2 CH2. So if there will be less more number of CH2 unit is present into the polymers, so that become your polymers is more and more flexible. So more and more flexible means that polymers needed less energy to move. So if polymers become more and more rigid, so you need much more energy to to uh, to like become that glassy to rubbery changes. So like polyethyl methacrylate, which is much more rigid, so it needs TGH around 65 degrees centigrade. Poly-N propyl methacrylate is 38 degrees centigrade, but polybutyl methacrylate, that TG temperature is minus 2 degrees centigrade, because that butyl means that number of CH2 is unit is high, so it become more flexible, the TG is lower down. So then you have to predict that how much TG of that polyisopropyl methacrylate. So isopropyl means your the CH3 is here. So it should be between this, like in when you're talking about the CH2 like this, and if you're talking about the polypropyl, so there will be 3 CH2 is present. But in isopropyl what will happen, so it will be like look like this. So one is that some isopropyl is group is there, so it will be not that much rigid as compared to this that methyl one, because it's some CH3 units, so that become less rigid, because when there will be CH2 unit, so it will be become more rigid because their packing is more better. So more better packing into the polymers, so it will be needs more much more energy as compared to when there will be less packing. So it will be little bit flexible as compared to that CH2 but not that much flexible as compared to that propyl one, so that its TG should be in between this methacrylate and ethyl methacrylate and N propyl methacrylate. So if the in between the TG, so only this that one option is present, so like that 50 degrees centigrade, so the TG is around 50 degrees centigrade for this material. Now the question number 7, it's tells that estimate the glass transition temperature in degrees centigrade of random copolymers vinyl chloride and vinyl acetate containing 48% of vinyl acetate. The TG of polyvinyl chloride and polyvinyl acetate whom polymers are 88 degrees centigrade and 32 degrees centigrade. respectively respectively. So you have to estimate that glass transition temperature of that copolymer. So we want to use this Fox equation. So from Fox equation what we get that the Tg of the copolymers. So Tg of the copolymers will be depend on that weight fraction of that polymer A plus,
Sir,
yes,
uh, 0.4 divided by 305. 305 is the common value always.
no, it's not common value. So it will be Tg, you have to convert into its Kelvin. So here that Tg is given at 88 degrees centigrade and 32 degrees centigrade, right? So if you convert this 32 degrees centigrade into Kelvin, so it will
Okay,
be
sir.
273 plus 32, right? If you want to convert into that Kelvin, so it will be
Sir,
become,
once again.
305 Kelvin. So in that Fox equation, you have to always that put this temperature in Kelvin. So now from here you are getting temperature in Kelvin. So how much you are getting? Then you have to convert into this into degree centigrade. So it will be coming around, if you calculate it, so it will be coming around 336 Kelvin. From here if you calculate it, it will be coming around 336 Kelvin, the Tg. So from there you have to minus it, minus 273 to getting this temperature. So it will be coming around 63 degrees centigrade. So minus. So from here you,
Sir, I don't understand, sir. Please explain.
okay. So this equation you know. So in this equation where we are putting, so always you have to put this in Kelvin scale, right? So Tg of A is given 32 degrees centigrade. So if you convert into Kelvin, so it will be coming around 305, right? That you understand?
Yes, sir.
Okay. Now Tg of B is given 88 degrees centigrade. So if you convert it into Kelvin, so it will be coming around 273 plus
Sir,
88.
where is 361, sir?
So it will be coming 273 plus 88. If you add it, how much it will be coming? 361, right? 8 plus 3 is 1, 11, then 6, then 2 plus 1, 3. Right? This will coming. Did you understand?
Yes, sir.
Okay. And now here the copolymers between that vinyl chloride and vinyl acetate. And they are told that vinyl chloride is containing the 48% of vinyl acetate. So 48% means 40 divided by 100, right? So it will become 0.4. So 0.4 is your vinyl acetate in that polymers, right? Because it tells the 48% of vinyl acetate. Did you understand? No? Hello? So that here tells that in the copolymers there will be 48% of vinyl acetate. So that if the weight fraction of vinyl acetate how much? So if you write is that W of vinyl acetate, like if you're putting like VAC. So the 48%, that means that weight fraction is 40 divided by 100. So it will be coming 0.4. So total polymer is 1. In between that 0.4 is your vinyl acetate. When you're talking about the weight fraction, so weight fraction means that overall weight is 1, so in between that will be zero point 0.4 your vinyl acetate. So rest of your will be polyvinyl chloride, so that will be 1 minus 0.4, so it will be coming 0.6. So now if you put into this equation 1 by Tg of copolymers, so first for that vinyl acetate, so vinyl acetate, the temperature given here for the homopolymer is 32 degrees centigrade. Then you convert this 32 degrees centigrade into Kelvin, so it will become 305. So it will be 0.4 divided by 305. Then the second one is that vinyl chloride, which is the 68%, that means the zero point 0.6 divided by its Tg temperature. So if you put into that Kelvin scale, it will become 361. Now you put this into the equation 1 by Tg of copolymers equal to 0.4 divided by 305, 0.6 divided by 361 for the vinyl chloride one. So this one for the vinyl chloride and this one for the acetate. Right? Then you are getting the temperature, it's like that 336 Kelvin, around like that. So now you have to minus it to become in that into the degree centigrade. So if you minus it, so it will become 63 degrees centigrade. So it's around 63 degrees centigrade you are getting. So this will be your answer. So first you have to make the degree centigrade into the Kelvin, then you have to convert that Kelvin to degree centigrade, and you have to know about that how much what fraction of polymer A and polymer B present into that polymer blend or copolymers. Now the next question is, consider the following two polymers with similar molecular weights. Which of the following statements is correct? So in between you have to measure that which is that needed higher energy. So which is more rigid and which is more flexible. So if you show that polymer A and polymer B, in between this that CH3 is present here. The two CH3 is present here, and here only one CH3 present. So if you pack this polymer, so this CH3 are always present in the two side, but here the possibility of presence of CH3 may be one side, then in another polymer so it will become other side. So for this reason, when there will be only CH3, then that packing of this polymers are not that much good. So for this reason, the polymers B have that packing is not better. Polymer A have that better packing. So polymer A is more rigid structure, while the polymer B is little bit flexible. So polymer B is thermally less stable as compared to the polymer A. So if you compare the crystallinity, so when there will be more packing, so that will be more crystalline, so that the polymer A is more symmetric. So polymer A is more crystalline as compared to the polymer B, because the polymer B is asymmetric due to the presence of one CH3 unit into that polymer. Now the next question on decreasing each of the following, which one will be generally increases for the Tg of the copolymer. So Tg of copolymer also we can increase or decrease by choosing some additives into that polymer. Like a polymer, like to make a polymer a final material, so like hose or something, so you want to add some additives into the polymers during that polymer processing, like you want to add some color agent to make that looking it's good. We add some additives to, like some silica or some cross-linker agent, to becomes that polymers become more and more hard. So depending upon that material what we are going to use into the polymers, that polymers property are different. Like if you were use some additives like which is hardening the polymers, so that become the polymers become hard materials, the TG of the polymers will be losing. But when we add some plasticizer, so plasticizer means you are add some materials which increase that free volume of the polymers, and when you are increasing the free volume of the polymers, so that polymers become more and more flexible. So if you add some plasticizer, then the polymers become more and more flexible. So when your polymers become more and more flexible, that times your TG is decreasing, right? So how you can decrease your TG of the polymers? So you have to add some plasticizer there. So number of polar groups present into the polymer backbone. So if you increase the polar groups, the polymers become more rigid type. Stiffness of the polymer backbone, if you increase the stiffness, the polymer become more and more rigid, so the polymer TG will be increases. So you can add some plasticizer there, so increase that, decreasing that TG of the polymers. Molecular of the polymers, sometimes with increasing the molecular weight, your polymers TG not affecting that much. So here the right answer will be concentration of plasticizer, which was you increase, you decreasing the TG of the polymer. Now this is the equation of the thermodynamics. From here we get that, that when it will follow the first order kinetics, like for that melting temperature, it will follow the first order of Gibbs free energy, and when it will be coming that TG, so it will be for the TG. So this also called that coefficient of thermal expansion coefficient. So it will be given by this Cp value, so which is due to this Tg, that second derivative of Gibbs free energy. So in that first order transition, like for the Tm, so they are only changing that state, which is called first order transition. When there will be not changing in state, it will be happen that second order Gibbs free energy, so that will be called that Tg. So which is the following thermodynamic, last question of today's. So which of the following thermodynamic parameter changes discontinuously on heating of the polymers beyond its Tg or glass transition temperatures, like volume, enthalpy, entropy, coefficient of thermal expansion. So from this equation you clearly shows that this thermal expansion coefficient, which is changing with that Tg, so it should be that last one would be the right answer. The glass transition temperature is related with the coefficient of thermal expansion. Okay. So today's class is up to this. So next we meet in the next week for another problem. So up to this, do you have any doubt? If not, then so we are stopping today's class. So we'll meet in the next week. Okay.